Right, so I'm going to say welcome, and we'll start this lesson. And this lesson is going to be on the electron configurations and the periodic table, and that's going to be pretty much all of 3041. So we're going to be going through quite a bit of the lesson, going quite fast through this lesson. So let's see how far we get. Any questions before we start? No, I see nobody's typing. Okay, so let's go for it. Okay, last year at level 2, or when you last at level 2, you learned about the energy levels. Do you remember that? Energy levels in electrons, in atoms? So you can say yes or no idea what I'm talking about. Yep, okay. And you came across something similar to what you see there, a nucleus in the middle and then a whole lot of layers, if you like, little circles, each representing an energy level. Now that's actually quite a simple thing, and really in reality it looks more like that. So it's a whole lot of different levels, not just four levels or 5 levels, it's lots of little ones. And these are what we call the sub-levels. Now you're never going to see something like that second layer, so it's much easier to represent what I'm showing there now. So we've got really the first energy level has got no sub-levels, it's just one. Okay, it will feel like there's one sub-level in the energy level and that's it. The second energy level splits up and it has 2 sub-levels. And I'll explain the reasonings why we know this. And then level 3 has got 3, level 4 has got 4 sub-levels. How many sub-levels do you think level 5 would have? 5. Okay, so you get the idea. There's actually never been anything with no energy level 5 yet, but who knows, they may make an atom that big. So what we say, an energy level N has N sub-levels. So if N is 1, it's got 1 energy level. So if it's first energy level, N is 1 energy level. N is 2, it's got 2 energy levels, and so on. Now notice, have you seen this K, L, M, and so on before? Yep, you have. Okay. It's an old-fashioned way, but it's still used a lot. The reason why it starts at K is when they were finding out all this, and it was working together with atomic spectroscopy, they thought they would find out a whole lot of more. So they left A to J for future discoveries, and they started at K, and that's the only reason why it starts at K and not at A. As a matter of interest, I just want to check, I'm trying to see if I write on here. No. Oh yes, I can. So I can actually draw one here, I think. So I'm just trying something out that I haven't done before. Okay, so yes, so there's a K, oops, I've got to learn how to draw here, L and M shell. So a shell is like an energy level, it's the same thing really. Shell is an old term, energy level is more of a new term, but either are acceptable. Right, so we've got this idea of energy levels and having some sub-levels. Now in each sub-level, because we're just talking about energy, but to find out where electrons are, we talk about orbitals. So this old idea of electrons orbiting the nucleus like planets orbit the sun, it's an old idea. They don't necessarily do that. It's just because electrons are small, we never know where they are, how fast they're going at the same time. But by using mathematics, they can find out the areas where it's most likely to find an electron, and that's what we call an orbital. So all what an orbital is, it's the area or the region you'd most likely find an electron. If you wanted the fancy definition, it's because it's all done mathematically. It's a wave function that describes what an electron with a given energy is doing inside an atom or molecule. But don't worry about that one. Just think of it as an area you find the atom. They have different shapes depending on what energy level they're in, what sub-energy level they're in, and so on. So those are some of the shapes you can have, and they're called SP D, and F. So you can get s orbitals, p orbitals, d orbitals, and f orbitals. If you can see, the s orbital is, is a round shape. Okay, the p orbitals, they've got one node. Sorry, can you? But yeah. They've got one node there. I was trying to draw an arrow, and it doesn't show it very clearly, or a gap. And as you go to D, they've got two. How many gaps do you think F would have? Three. Yep. As I say, you do not have to know the shapes. I'm just trying to sort of give you an idea of what they sort of look like. And again, the SPDF, I know a student asked me last year, what on earth do they stand for? It's old terminology. When they were looking at spectroscopy, it came from, they had sharp lines, principal lines, diffuse lines, and fundamental lines. That's just where those SPDF come from. But otherwise, forget about that. So, what you do have to know is how many orbitals you have in each sublevel. So, with the s orbital, you only have one. P orbitals, you get three of them. So d orbitals, I think you can see the pattern. This is a pattern that's been going on all what we've done so far. How many d orbitals would you have? If you have one s orbital and three p orbitals, how many d orbitals would you get? 5. And f orbitals, you'd get 7. Okay, so you see that pattern. Great. So if we look over here, the first sublevel has one s orbital. So first energy level has only got one orbital in it, and that's the s1. The second sublevel would have p orbitals in it, and there are 3 of them. And then the third one would have 5 d orbitals, and the fourth one would have 7 f orbitals. You, as far as NCA goes, forget about the f orbitals, you don't use them. Okay. The next thing you have to do is work out the number of electrons, because we're trying to work out where all these electrons fit inside the energy levels. So we can have a maximum of 2 electrons in each region, in other words, in each orbital. So if you have a region where you're not going to find an electron, we're going to have a maximum of 2. Now, why 2? What can you tell me about the charge on an electron? So I see, Andrew, it's negative. Correct. Now, if I've got 2 negatives together, what are they going to want to do to each other? They repel. So if I have an electron in one region and I put another one there, they're going to want to repel each other. However, the electrons not only, now we can use a planetary model. If you think of the Earth going around the Sun, the Earth is going around the Sun, but what is the Earth also doing as it's going around the Sun? So the Earth has got another type of movement as it's going around the Sun. It's not just, it's turning, it's spinning. And electrons do exactly the same thing. Now, electrons, because they are charged, if you've done any physics, a moving charge will create a magnetic field. So because the electron is spinning, it actually acts like a little magnet. So what I've tried to show in this diagram over here is one electron is spinning in one direction and the other one is spinning in the opposite direction. So can you see they're like 2 little bar magnets, with one where the south pole is on top because it's spinning in one direction, and the other one because it's spinning in the opposite direction, there's a north pole on top. So what can you say about those 2 electrons now? Will they repel? No, because although the charges are repelling each other, the magnetic field around them is causing them to attract, so they can actually be in the same area. If I try to put a third electron into that same area though, what do you think is going to happen? I see you both typing. There'd be an unbalance, yes, because if I put a third electron in, the negative charge is going to repel, and it's going to be either the north on top or the south on top, so that it's going to repel one of them regardless. So the maximum we can have, electrons we can have in an orbital or a region where you'd find an electron would be 2. You'd never get more than that. So if we've got a region or an orbital, it can be empty, or it can have 1 electron in it, can have 2 electrons in it, but it can never have more than 2. So is that clear? Okay, now we're going to sort of start putting it all together, because I know we've gone through a lot of things. We've gone through energy levels, sub-levels, and we've looked at orbitals. The shapes, by the way, are not important. I just really more for interest. But the important bit is that the orbitals can have 2 electrons. So the maximum number of electrons in each energy level can be worked out by the formula of 2n2. So if it's the first energy level, 1 squared is 1, 1 times 2 is 2. So the first energy level only can have 2 electrons in it. The second energy level, if n is 2, what is 2 squared? 4. And 4 times 2 is 8. Correct, Hannah, you're jumping it. Well, Hannah, you're jumping it already here, so that's great. Is this starting to make sense with the electron configurations you did last year of 2, 8? Now the next one's a bit tricky because we're going to come across the d orbitals, which you have not used before at level 2. The third energy level has got 3, so 3 squared is 9, and 9 times 2 is 18. So the third energy level can take 18 electrons. Now in the past you've done 2, 8, 8, and that's because you've only ever gone up to the first 20 electrons, and the d orbitals were not involved. So we're going to look at it now, or very soon. This is just a table to summarize. The first energy level, you'll notice if I draw here, so over here, the first one, it's got a maximum of 2 electrons. We've worked out it's got 8 for the second one, 18 for the third one, and 32 for the fourth one. You don't really come across the fourth energy level at all, apart from you go up to 4p, and that's about it. Notice in the first energy level, you've only got 1 type of orbital, that's the s, only 1 sublevel. The second energy level has got 2 sublevels. Remember, it was the same. The number of sublevels was the same as the energy level number. The third energy level has got 3 sublevels. And remember, the first sublevel is S, the second sublevel is P, and the third sublevel is D. And then the fourth one has got S, P, D, and F. And then if we work out the total number of orbitals per energy level, we've only got 1 orbital in the first energy level. We've got 4 in the second. 3 plus 1 is 4. And you'll notice we've got 9 in the third one, and we should have 16 in the fourth one. Does anybody want to come up with a mathematical formula of working out the number of orbitals per energy level? When we looked at the number of electrons, so the electrons, we said it was 2n squared. What do you think the number of orbitals per energy level would be? Okay, see Andrew's typing, but it's not that important, but it's useful. Oh, okay. So it would be Well, it's just simply n squared. Because remember, there's a maximum of 2 electrons per orbital. So you'll notice 1 squared is 1, 2 squared is 4. So you've got a total of 4 here. You'll have a total of 9 orbitals over here. Sorry. Oh, I can't write. Let me just click this out. Sorry. I'm still trying to learn how to use this fancy gadget I've been given. Right. Okay. So we should have a maximum of 9 here. And we should have a maximum of 16 orbitals over there. Okay. Right. So Andrew, you've come up with a complicated one, but it must probably works too, but it's just saying n squared works just as well. Right. And as I was saying, that was what I said earlier about A to J was set aside for future discoveries, if you were wondering why I started with K. So let's have a quick quiz. True or false? Each s orbital can have 0, 1 or 2 electrons. True or false? Just say T or F. True. Okay. Right. The third energy level has S, P, D and F orbitals. False. Correct. It only has got 3. Remember, third energy level only has 3 sublevels, so it can only go up to SPD and SPD. The second energy level can hold up to 18 electrons. So think of 2n squared. False. Correct. So 2n squared, it can have a maximum of 8. And the number of orbitals is given by 2n squared. False or true? Type in, okay, it's false. It's okay, it's false because the number of electrons are given by 2n squared, but the number of orbitals is n squared. But I know that this can be confusing between the two. Now, if you have a periodic table handy, and I suggest you always bring it along in these lessons because you will also get a periodic table in the exams. So have it handy, and it's really useful to work out the where the electrons go, because electrons will always go to the lowest possible energy level first. So remember, in my first energy level I can only have 2 electrons, so the first electron will go into the lowest energy level, the first one, and because it can take a maximum of 2, the second electron will go there as well. Then the third electron will have to start moving into the second energy level, so it's like the second row of the periodic table. So it goes into the second one, and remember each orbital can have 2 electrons, so that's where the fourth electron goes. Now the s orbital in the second energy level is full, and now we start putting them into the p. Now notice we make them, I'm pointing them upwards, I'm representing the arrows as electrons, they're pointing upwards. It's to show the spin. They spin in one direction, they each go into the separate p orbitals before they'll start spinning in the opposite direction and start pairing up. So that's the reason for the up and the down arrow. And then you'll notice I'll go into the 3s orbital and then the 3p as you'd expect. And then I start with the 4s. Now notice what happens now with the 4s. We've done the 4s before the 3d, because actually 4s is lower in energy than the 3d. So it's 4s first, then we fill up the 3d. Oh, and I should have gone to, okay, I thought I'd filled up for the rest, but so we're obviously gone, but you can fill up all the way to the end of that row. Now, a really good way of looking at where those electrons go is in off-bar diagrams, and in OTL there's a lovely one there. So I'm going to look at this now. Now I hope you can see this. Now I can't see your chat at the moment, so we're just going to have I'll explain it and then I'll minimize. This is showing the first energy level. It's just got 1 electron, 1 orbital in it. This is the second one. This is the third one. And it's not very clear. The 4s should actually be lower in energy than the 3d. So if I want to fill it, there's my hydrogen. It has got an electron configuration, and we'll explain that and how it works. But notice 1 is for the energy level, S is for the orbital, and that little superscript 1 is to show how many electrons are in it. So hydrogen has an electron configuration of 1s1. It's sitting the lowest possible energy. Helium would be 1s2. And then if I carry on, lithium is 1s2, 2s1. Beryllium, you can see it keeps on going up, and it just adds up. And you'll notice the neon has got a full energy level, because remember, it can take a maximum of 8 electrons in the second energy level. 2s squared, maximum of 8. When I get to sodium and magnesium and then aluminium, I'll just go through these quite quickly. Notice now the electron configuration has changed a bit. This is what we call the noble gas configuration, and I will explain that. Just look though at this last, the 3s2, 3p1, and notice how as we add electrons, the electron configuration increases until we've completed to argon, the noble gas, and that is full. I know the d orbitals haven't been filled yet, but neon won't react because it doesn't have anything in the 4s, which gets filled first before 3d, simply because it's lower in energy. And as I say, this one thing with this diagram, it doesn't show it very clearly. The 4s should have been lower in energy than the 3d. Right, I am going to now carry on here. We're now putting it to the 3d. Notice how the spin is always going in one direction. And look carefully what I've got here for vanadium. 3d3, 4s2. Now, if I go to chromium, you would expect it to go to 3d4, 4s2. Because if that's scandium, it's 3d1, 4s2, titanium is 3d2, 4s2, vanadium is 3d3, 4s2. So you'd expect chromium to be 3d4, 4s2. But it doesn't. Notice it's changed to 3d5, 4s1. That s electron hopped in to fill this. And the reason is a half filled or a completely filled energy level is lower in energy. The energy actually drops. We'll see it in the next one. So you'll notice when I go to make manganese, that fills up first, the 4s, because the 4s always wants to get filled first. Then we go to iron, cobalt, nickel, and the same thing is going to happen for copper. This gets filled up, that electron hops over to fill it up because it gives it a lower energy. So those two exceptions, chromium and copper, they're fairly easy to remember because they're transition metals. They're this middle bit, and they're the two of them that are starting with C. I know there's cobalt as well, but two of the three are the ones that are the unusual one that you have to learn off by heart. And just to finish off, I can just gaily go on and finish up with krypton. You have to be able to write the electron configuration for any for anything up to the krypton energy level. So that is one way of looking at it. It's nice seeing it there and seeing the electron configuration. Use the periodic table in the same way, and remember the chromium and the copper. Any questions so far? Okay. Now, right. Okay. What we're going to look at now is okay. So to follow the order of the periodic table, you've got to show the number of orbitals for each sublevel. So it was, remember, it was 2s, 2p, 3s, 3p, you've got to write those in. And then you add to the lowest energy first. Right, correct. And then you add the electrons singly before they get paired up. And because that helps explain why your chromium has that funny electron configuration where it's changed. From 4s2 it becomes 4s1 and then it goes to the 3d. Okay, so that's a really important thing about noting the anomaly. They often ask, they don't ask it every year, but they ask it more often than not. They'll ask you for the chromium or the copper electron configuration. Now, let's have a look at this one. This is just very briefly to show that drop in energy I was talking about. So I'm going to just quickly add a new so I'm going to just quickly share my screen. And hopefully you'll see this now. So this one, really what I want to show here is, this is showing the energy, and I want you to see how the energy changes. So as the orbitals go lower down on over here, it means it's dropped in energy. And remember, the less energy, the more stable. Okay? All the electrons want to be couch potatoes. They want to just sit on the couch and do nothing. They don't want to be jumping around. So if I have hydrogen, that's got quite a high energy. If I go to helium, it fills that orbital, and did you notice that drop in energy? And it's that drop in energy that makes helium less reactive than hydrogen, because it doesn't want to now go up and do anything. Lithium has that extra one, and can you see how that first energy level has dropped even further because it's even less energetic, and that extra electron has got enormous, much more energy than the lithium. The beryllium, it's paired up, so it drops a bit. Now I get to these, and as I start pairing up and I get to neon, there's that drop again. So this is what I was explaining when I have half filled or completely filled orbitals. There is a drop in energy. Can you see sodium? There's a big drop again. If I go to magnesium, a slight drop, and suddenly it goes up again in energy. And as I pair up and I get to argon, there's that sudden drop. So that's just to show you why something is unreactive when it's got, say, the noble gas configuration. You don't have to otherwise learn that, but it's just that background understanding. What you have to do in the exams is be able to write electron configurations. And so I was just trying to explain there why the chromium and the copper have that anomaly in that slide. Okay, we've gone over the electron configuration of how to do it. So basically, each energy level is written before the orbital letter. You've got to use superscripts to show the number of electrons in each orbital. And you always write them from lowest to highest in energy. It could also be in order of energy levels. NCEA accepts both. In other words, you could say 1s2, 2s2, 2p6, 3s2, 3p6, and then either do 4s2 before you get to 3d, or you could do the 3d first. I know in some places they want you to do it in terms of energy. Okay, now to check if you made a mistake, add all your electrons up. So add the two, so just showing over here. So 2 plus 2 is 4, plus 6 is 10, plus 1 is 11. You've got 11 electrons. So for a neutral atom, how many, or what atom are you using? What has got 11 electrons? What element? Do you know offhand? Sodium, correct. So if I've asked you to write the electron configuration for sodium, count up your numbers to see if it gets to 11. If it doesn't, you've made a mistake. Right, so we're running a bit out of time if I want to do periodic trends because we're halfway through the lesson. But very briefly, I'll explain why some of these are correct or incorrect. The first one is incorrect. Okay, if you add up sort of those electrons, it's 2 to 5 makes 9, and remember your 9 is the atomic number, so it does add up. But what is wrong with it? Why is the first one incorrect? It's not the how many numbers, but where they are. So Hannah is typing, so I'm just going to quickly move on. Okay, Hannah, is that what you wanted to say? That, yes, you need to have superscript numbers. So don't make them the same size or subscript. They have to, the number of electrons must be shown as superscript. Chromium, okay, that I hope you can see is correct. It's 4s1, 3d5, because that half-fold energy level is lower in energy. Sulfur is also correct, 16. If you added up all those numbers, it's sorry, it's actually false, sorry, because, and I'll just point this out in case you don't see it, I haven't put the 3 in front of the p's. You have to, before each orbital, write the number. So don't go 1s2, 2s2, p6. It's got to be 1s2, 2s2, 2p6, and so on. And the last one is, if I remember, that's also, okay, that's an example where a student filled in the d orbitals before the s orbitals. So remember, 4s is lower in energy, so 4s gets filled before the 3d. Okay, then very quickly, the noble gas configurations. You basically take any noble gas preceding the element and put it in square brackets. So square brackets are used a number of times in chemistry, and this is one of the cases. And then you follow the normal way. So if I took this example, this is calcium. So if you've got a periodic table in front of you, you'll notice that the one in front of that, so those numbers in blue are is the electron configuration for the argon noble gas. So you could just put AR in brackets and then 4s2. Now I recommend you write out the full electron configuration first, so that you can add up those numbers to check that you've got the right number of electrons. And when you're confident and you're not making mistakes, then you can start using the noble gas configuration. Both are acceptable in the exams, unless they specifically tell you not to use the noble gas configuration. Right, and then this, I'm just going to quickly say, okay, oxygen, the preceding noble gas is helium, copper, the preceding noble gas is argon, and remember it's at anomaly, so 3d10, the 4s1. Aluminium, it's neon. Bromine, it's argon. Nickel is also argon. Okay, and that's just because we're running out of time. Now cations and anions, to do the electron configuration, it's exactly the same, but now when we count the number of electrons, we have to either subtract the charge or add the charge. When do we, oh, actually you may not understand what I mean by subtract, so let's do an example. So if I've got a cation and say calcium has a charge of +2, calcium has got 20 electrons, so do I add the +2 or do I subtract the +2? In other words, do I land up with 22 electrons or 18? I subtract, correct. So the one I've given there is sodium. So if I have sodium element, I've got 11 electrons. So it goes all the way to 3s1. But if I've got the sodium ion, and you've got to be very particular which ones you're using, put up in a plus to show you doing the sodium ion. It's the same as the noble gas configuration. It'll be 10 electrons. And if I have anions, it's going to be add on the charge. You've got now more electrons. So if I had oxygen, oxygen has got, oh, I've made a mistake. I've left the 11 there. Sorry, that's a mistake, that 11 for oxygen. Oxygen has got 8 electrons. And So you would expect it normally to have 8 electrons, but if I have the iron, the oxide ion, it's going to have 2 more electrons, so it'll have 10 electrons. So just very quickly, if I did that with the transition metals, because these are the tricky ones, and they basically always get asked what are the transition metal ones. The electrons go from the valence energy level, not necessarily the highest energy level. It's normally the same thing, but it's from the valence, the outermost energy level. So will you get your electrons removed from the 4s or from the 3d first? Which one is the outermost energy level, the 4th one or the 3rd one? So see, nobody's really wanting to have a go. But if I take my iron, for instance, it's got 24 electrons. So what I've written over here is for the neutral atom. When I take away my electrons, the 4th energy level is the valence energy level. So I've got to take from the 4th energy level before I can take from the 3rd energy level. So I know the 3D are higher in energy, but we're looking at the valence shell, if you like, using that old term. So my Fe2 plus is going to have the 3D, it'll be 3s2, 3p6, 3d6. The 4s has gone. The electrons move from the 4s first. That's, I suppose, the trickiest. I tend to use a, why is this not working? There. So it goes from the 4s first, and I use this little poem to help remember. First to fill, first to flee. So the electrons go first in there and they get removed first from there as well. 4s first, then 3d. So the flee and d hopefully rhyme and help you remember. So you put it into the 4s first, but then when you've got your atom and you've got to remove electrons, you take them from the 4s first. Okay, so that's a common error when people take from the 3d first. It's from the 4s. So we have again over here this electron configuration. Okay, I'm going to do this one to ionize. So if I, for instance, have calcium, there's calcium with the 4s electrons, and so when I ionize to make the cation, notice they've gone from there, and it's the same as the noble gas configuration. If I go to, for instance, vanadium, there is a 3d3 4s2. Now if I ionize it, oh sorry, that's not, there's no common ions formed. Let me use the Fe, the one we were looking at. So the 4s, and then we've got the 3d. If I ionize, notice that the 4s has gone first. So I can ionize again because iron forms Fe2 plus as well as Fe3 plus. So that's for the Fe2 plus ion. For the Fe3 plus ion, you can see why iron has got that ion formed, the Fe3 plus, because of the stable 3D configuration. If I take copper, copper has got that full. If you can get the copper 1 ion, so you can, oh, okay, this one doesn't show it, but the copper 1 would have gone here. This is formed the copper 2 plus. Zinc, you know, only forms the Zn2 plus, and that's because it only loses the 4s electrons. So these links are opal. Have a play around and see what you get. Take sulfur, for instance, because it goes the other way. Sulfur is short of filling up, but if I ionize, then can you see that that has filled up? I have added electrons. So that is quite useful to play around with and to see what's happening. Any questions on writing ions. As I say, I know I'm moving through this quite quickly. Okay, so remember that 4 is, first of all, 4 is first, then 3D. And I'm just going to flick through these. Yes, electron configuration is different to oxidation numbers. Oxidation numbers are theoretical numbers. They are not actual charges. Electron configurations just simply tell you where the electrons are and in which orbital. So you can only do it for proper ions. You can't do it for a theoretical ion. Right, so this, if you were watching a recorded video, pause it and see if you can do the answers. Otherwise, I'm just going to give you the answers now. Notice the copper 1 ion, I've lost the 4s electron. With the Fe3 plus ion, I've lost from the 4s as well as 1 from the 3D. The aluminium has lost all the 3s and 3p electrons. Bromine, it's added 1, and the calcium, it's lost from the 4s. Right, periodic trends. I don't think we're going to finish this session, and I know we are hurrying through it quite quickly, so you're welcome to ask questions. Those are the trends you have to know, but it's not going to be enough just to know them. You have to be able to explain them. So how big the atoms are, they get bigger and bigger as we go down, and they also get bigger and bigger as we go from right to left. So this down here is the biggest atom, and this up here is the smallest atom. Okay, hydrogen I know has only got 1 electron, but helium, because it's got more protons, it pulls those electrons more closely, and we'll go into that. The same thing with ionization energy. Ionization energy is just simply the energy needed to remove 1 mole of electrons from a mole of the gaseous atom. So you've got to first make the atom into the gaseous phase, and then remove the electrons. And as we go across, it gets harder and harder to remove 1 electron. I think you'd realize it would be quite hard to remove an electron from Cl, because you know you can get Cl minus, but have you ever heard of Cl plus? Is that common to form Cl plus? No. Okay, so it gets harder and harder as we move across, and it also, it gets harder as we go up, or it gets easier and easier as we go down. So basically, it's the easiest to remove an electron from down here, and it's the hardest to remove an electron from up here. That explains fluorine, why fluorine hangs onto its electrons so much. It's very hard to remove from it. And it also explains why the noble gases don't like sharing, and they don't want to do anything. The ones down here, though, you can force them to share with something like oxygen. So you do get some compounds. You'll notice you have to write some compounds with xenon, and that's down here because you can make it share its electrons more easily. Now, electronegativity, it's the attraction an atom has to its bonding electrons. So it's only in molecules where it's bonded covalently. So we don't talk about electronegativity for ions, we don't talk about electronegativity for compounds, or even actually for molecules, because it's a property of an atom, or an element, if you like, an element in a molecule. That's the only time we use electronegativity. And you will actually be using it a lot for this exam. So let's go and explain, because this won't even get you achieved in this particular question. You can know all of that, but if you can't explain it, you're not going to achieve it. So that's the important bit. Now, the background explanation is really on Coulomb's law. Who's come across Coulomb's law, say, in physics? Has anybody done that? No? Okay. Right. You do not have to know the formula. Okay? But what I'm trying to explain here is that Q is this charge and D is the distance between the charges. So can you see the bigger the charge, what can you tell me about the force of attraction? So that's the force of attraction between the nucleus and the valence electrons, and this is the charge on the nucleus and the electrons. The bigger the charge, what can you tell me about the force of attraction? Will it be bigger or smaller? So Hannah's typing bigger. Correct, Hannah. But notice this is an inverse relationship for distance. Okay, it's 1 over d2. So the bigger the distance between the nucleus and the electrons, what can you tell me about the force? It's now an inverse relationship. Inverse means opposite. So it's smaller. So if you remember that, you are pretty much all that. If you remember, you talk about charge size and you talk about distance, you will definitely get achieved. Okay? So there's an example of my protons and my electrons, the distance between them. So the bigger the charge, so the more protons we have in the nucleus, the bigger the force of attraction of the nucleus on the electrons. Okay? And the other option is, of course, the further the nucleus is from the valence electrons, then the weaker the attraction, or the way I've written there, the closer the charges are together, the stronger the attraction. Okay, so let's talk about the atomic radius. We can only sort of measure, an atom is too small to measure, so the only thing we can really look at is molecules, and we can try and work out what the atomic radius is by halving covalent bonds and fiddling like that. A lot of people have spent a lot of time trying to get approximate sizes for atoms. So if I took half the distance between the two nuclei, I'd have the size of the iodine molecule, iodine atom. And to explain, say, the iodine atom size to the fluorine or the bromine atom, I need to mention all these points. They're based on that Coulomb's law. And the easiest way to remember is to think of pens. Okay, you've got to talk about periodic trends, so think of pens to rhyme with it. So P, protons. Talk about the number of protons. Okay, how many protons? Because that's going to affect the charge, and the N for pens is the nuclear charge, the charge on the nucleus. E stands for a number of things. The energy levels, how many energy levels have I got? How many electrons have I got? And the effective nuclear charge. I will explain that. The effective nuclear charge differs from the nuclear charge because of this thing down here called the shielding. Sometimes there's something in the way between the nucleus and the valence electrons. But otherwise, all those points you have to talk about. So let's, I was just trying to show that's the distance between the protons and the valence electrons, and that's going to influence the force. Okay, right. This is the type of answer you've got to give for an explanation why the atomic radius changes across a period. So if I'm comparing, say, sodium with chlorine, you can't just say chlorine is smaller because it's on the right-hand side of the periodic table. You wouldn't even get achieved for that. You do need to explain. So the important bits, do you see those pens there? The P for protons, the N for nuclear charge, the E comes up in electrons, energy level, and then I'll explain the shielding now. Okay? So what you've got, if I show these diagrams, the first diagram is for lithium, right? Lithium, oops, didn't come out very clearly. Lithium has got 3 protons. So my nuclear charge is 3, or it's approximately 3. It's not quite 3 because can you see I've got electrons in this area, and it's a bit like a magnet. If you want to stick something onto the fridge, so you've got a piece of paper, you put it on, and then you put a magnet there. It'll stick one piece of paper. But as I add more and more pieces of paper between my fridge magnet and the fridge, will those pieces of paper stay on the fridge or will they all fall down? Yep, no, they won't stay in the fridge, they'll fall down. And that's because the paper is shielding, it's sort of forming a break between the fridge magnet and the metal that it's trying to attract. So this is what I mean by shielding. Look at how many energy levels are between the valence energy level, which is the outermost one, and the nucleus. In this case, I've got one energy level, the first one, that's shielding. And in this example, I've also got this one over here, and I've also got exactly the same amount of shielding. So I've got the same amount of shielding. So if I've got more and more protons going from left to right, so from 3 for lithium to 9 for fluorine, my nuclear charge is increasing, and my effective nuclear charge is also increasing, because can you see my shielding is the same? So if you wanted, if you like, a formula, your effective nuclear charge is equal to, your nuclear charge subtract your shielding. So the more shielding, the smaller your effective nuclear charge. The more your nuclear charge, the more your effective nuclear charge. Does that make sense? Yep. So I'm increasing my nuclear charge, I'm getting more and more protons, I've got 9 over there. I've got the same amount of shielding, so my effective nuclear charge is increasing. So what I'm trying to show with this orange thing over here, I've got a much stronger attraction. If I've got a stronger attraction, what do you think is going to happen to those valence electrons? Are they going to get pulled closer to the nucleus, or are they going to go further away? Anybody want to have a go? They'll get pulled closer. These are stronger charge. So think of that Coulomb's law. If it's a stronger charge, they're going to get pulled closer together. Okay. So that's the argument for across a period. Notice I've highlighted also valence electrons. You're talking about the attraction between the nucleus and the valence electrons when you're discussing atomic radius. So don't just talk about electrons, be specific. We're not talking about these electrons over here, the core electrons. We are wanting to talk about the valence electrons on the outside. Right, down a group, that is the sort of thing you have to explain, so that would be an excellence answer. You're talking about the valence electrons, and can you see those pins on there? Protons, electrons, energy levels, effective nuclear charge, shielding, and distance. Okay, so if I was looking here for hydrogen, then lithium, then sodium, then potassium, can you see what's happening? I've got only one proton here, but I've got no shielding. In fact, my nuclear charge is 1. Okay, here I've got more protons. So you think, oh, there's a greater nuclear charge, and that's correct. But I've now got shielding coming along. Okay, that shielding doesn't stop it completely, so my effective nuclear charge has increased slightly compared to the hydrogen. But what can you tell me about the distance between the 3p, between the nucleus and the valence electrons? Is it a bigger distance, or the same distance, or the smaller distance than that? It's bigger distance, so it's further away. So think of that Coulomb's law. The bigger the distance, or like that, the bigger the distance, the weaker the attraction. It's like holding two magnets further and further apart. Eventually you're not going to feel any attraction between them because they're too far away. So this is what's happening each time. We are increasing the nuclear charge, but because we're adding more and more energy levels between them, so we're getting more and more shielding, we're only getting a slight increase in the effective nuclear charge, and that is actually negated by this bigger and bigger distance between the valence electrons and the protons. So actually the atomic radius gets bigger and bigger down the group. There's a weaker and weaker attraction between the protons and the effective nuclear and the valence electrons. And that argument is going to be pretty much exactly the same for the rest. So in the last 4 minutes, we're going to just whiz through it. This is the definition of an ionization energy. Remember, it was the energy needed to remove 1 mole of electrons from 1 mole of atoms in the gaseous state or in the gas state. So it's in kilojoules per mole. Kilojoules is the energy term, per mole is for each for 1 mole. So it's removing, I mean, I've only showed one atom. Can you imagine 6.02 times 10 to the 23 of them? So removing that number of electrons, how much energy does it take? And if you read through that, can you see it's nearly exactly the same? I've started it in exactly the same way. The only thing that's different is this final statement. So you have to just simply, you know, once you've learned the pattern, you can do it across to any one of them. So if you just have a look at that, the yellow shows the amount of energy needed as I go across. Because those electrons are being held more tightly, they're closer, as we explained in the previous one, it's going to take more energy to remove that electron. And that's why chlorine does not want to lose an electron, it would rather gain an electron, because it takes too much energy to remove an electron. And as I say, if you're going over this video later, you can pause it and read through it. So going down the group, it's exactly the same. The only difference is the final statement I make. Okay, but the explanation is identical. So it's the same sort of thing. As we go across, the electrons are further out, the valence electrons, not as strongly held, easier to remove. Now, electronegativity, that is the attraction an atom has to its bonding electrons. Now, this is why I put those valence electrons in red, because this is the one case when you do not talk about valence electrons, you talk about the bonding electrons. It's not looking at all the electrons on the outer energy level, it's talking only about those bonding electrons. How strong is the attraction to the bonding electrons? So what I've got here is an example of hydrogen over here and fluorine over there. Hydrogen, if you have a look, if they're sharing electrons, it's a molecule, so they're sharing electrons. It's got a nuclear charge of 1 and it's trying to attract those bonding electrons. Fluorine, remember, has got a nuclear charge of 9. It's got the shielding, okay, of that first, because it's got so many protons, its effective nuclear charge will still be a lot bigger than 1, even though it's got those bonding electrons further away. It's still, those 9 protons still count, so its attraction is much stronger. Fluorine is the strongest in terms of, or got the highest electronegativity. So if I carry on, oh, there I was showing, I've put highlighted in blue there. You can see the blue for the hydrogen is weaker than the one for fluorine. Fluorine attracts them a lot more strongly. And there I've pointed out, we talk about the bonding electrons. And also I'm highlighting it's the property of an atom, not a molecule. And notice it's exactly the same as what we've got before, except I now talk about bonding electrons, and my final statement is the same. It's a bit different. And the same thing for down a group. This is showing really, as we go across the row, that they're held more strongly because they're closer to the nucleus and all those things that I said before. So the attraction will be much stronger for bonding electrons for fluorine than there would be for lithium. And down a group, exactly the same, and we've actually over, so I'm just going to show that over there. It's the same thing. Hydrogen, because it's got a nuclear charge of 1, There's no extra energy levels for shielding. There's all the other ones. It's adding an extra energy level each time, so the effect for potassium is going to be a lot weaker, so it'll be much, potassium will have a much weaker attraction to any bonding electrons, which also explains why potassium is so much more reactive. Now this is just to show the electronegativity. What we're trying to show here is, because fluorine is more electronegative, it's holding those bonding electrons more closely to the fluorine. Hydrogen, because it's the same element in the bond, it's going to be equally shared. This is just trying to bring in the next lesson. Here, carbon, it's got a small electronegativity because it's got a smaller effective nuclear charge, so it's not going to hold on to its bonding electrons as strongly. Oxygen, having a high electronegativity, will attract those bonding electrons more closely, so there's an uneven sharing. And then finally, its ionic radius, which is the size of an ion. And really, if we're forming a cation, we're going to have a smaller cation compared to the atom, whereas an anion will be bigger. And you can argue the same way, but really for the anion, I've added another electron into the same shell. The protons stay the same, so what I'm getting here is repulsion between those two electrons. So all those electrons are going to repel, and so it spreads out and goes bigger. So that's really the key point here. The key point with this one is I have lost an energy level, so my valence electrons are now in the first energy level rather than the second energy level. So it's going to be smaller. I think that's fairly self-explanatory. And that was a term, you'll see that term in the booklet, isoelectronic, is when you've got the same number of electrons. I won't go into it now because we're over time. And that's just simply showing the different sizes. Can you see it's the same discussion? If you were watching the recording, you can pause it. And that's diagrams also in the booklet. Now I'll rush through that quite quickly. Do you feel as though you've understood that? Okay. If you like, go over the booklet, and next lesson, I know I've rushed it, please ask me any questions if you have any. Or if you're watching the recording, email me any questions and I can go over it. And I'll stop there and say goodbye and all the best for the remainder of the week, and see you next week.